Hello students, the topic that we are going to discuss today is moving charges and magnetism, NCRT section 4.7 and example 4.7 to 4.8. So this is disclaimer. The learning objectives. After starting this chapter, you will able to learn to calculate the magnetic field both inside and outside a current carrying conductor of finite thickness using Ampere's law. Understand how to determine the magnetic field inside and outside a long current carrying solenoid using Ampere's law. So index of topics that we are going to discuss today is example 4.7, NCRT section 4.7, the solenoid, and example 4.8. So let's do first example 4.7, which is based on Ampere's law. So figure shows a long straight wire of circular cross section carrying steady current I. The current I is uniformly distributed across this cross section. Calculate the magnetic field in the region R less than A and R greater than A. R is some arbitrary distance. So it means some arbitrary distance R, we have to calculate the magnetic field for R less than A, means less than radius. It means inside the wire, and for R greater than A, it means for distance greater than the radius of wire, means outside the wire. So this is the diagram given, figure 4.13. You can see there is a wire and you have to calculate the magnetic field inside the wire where R is less than A, and outside the wire where R is greater than the radius of the wire. Okay, so let's see what is the solution. So firstly, we have to consider the first case, which is R greater than A, means outside point. Any point where we have to find the magnetic field, the point is lying outside the wire. So the Amperian loop labeled 2. You can see in the diagram, there is an Amperian loop which is labeled 2, is a circle concentric with the cross section. Okay, so it is the circle along the cross section. It is shown in 2D in that figure 4.13, but in actual, it is in plane of cross section. Means it is like cross section is a circle, like it is the circle concentric with the cross section. Okay, you can imagine like this is a cross section. If this is a cross section, then it is a circle with the cross section, concentric with the cross section. Okay, so that Amperian loop, that is labeled 2, and this Amperian loop is enclosing and it is passing through a point where we have to find the magnetic field, that is outside the wire. So for this loop, length of Amperian loop is L equal to 2 pi r, since the Amperian loop taken here is circle. So the length of the Amperian loop will be perimeter of the circle, that is 2 pi into r, and here r is the distance of that point greater than radius, and it is at a distance r from the center of the wire. So IE is the current enclosed by the loop I. Okay, the result is familiar to basic formula we use for a long straight wire. Okay, in the previous lecture, in Ampere Circuital law, we have derived the formula for long straight wire magnetic field at a point at a distance of r from the long straight wire. So that result we are going to use here. So that is B into L equal to mu naught I, that we have derived yesterday. That was B into L. L is the length of the Amperian loop, equal to mu naught I. Okay, length here is 2 pi r, and the current enclosed here is the current enclosed by the loop. So total current enclosed by the second loop, second Amperian loop, that is labeled 2. is total I current. Okay, so the current enclosed by that Amperian loop is total I current. So B into 2 pi R equal to mu naught I. From here we can find the value of B. So value of B is mu naught I upon 2 pi R. Okay, so mark it as 4.15 A equation. Okay, so now you can see for a point outside the wire, if point where we have to find the magnetic field due to a current carrying wire, current carrying thick wire. Okay, so due to this current I flowing through the thick wire, which is uniformly, in the question it was given that it is uniformly spreaded in the wire. Wire is thick and current is uniformly spreaded in the wire. Okay, so the magnetic field at a point outside the wire is inversely proportional to the distance of that point from the center of the wire. So for a point outside the wire, magnetic field is inversely proportional to R. R is the distance of the point outside the wire from the center of the wire. Okay, so magnetic field is inversely proportional to R for R greater than radius of the wire A. Got it? First thing we have concluded. Now, second thing, now consider the another case, that is R less than A, which means distance point in the inside the wire at a distance less than radius of the wire, that is inside point. So Amperian loop is here is labeled as 1. Okay, so R less than 1 means R less than A means distance less than the radius of wire, that means point lying inside the wire. Okay, so Amperian loop is here labeled as 1. You can see in the diagram there is a Amperian loop inside the wire. That black circle bold line, that is the radius of the, that is the cross section of the wire, and that is A radius. But inside that black circle there is a dotted circle, dotted black circle. Okay, that is the Amperian loop, that is labeled as 1. Okay, so current enclosed by this loop, now current is uniformly spreaded through the whole wire, but Amperian loop having radius less than the radius of the wire. So current enclosed by the Amperian loop will be less than the total current I. Got it? Current I is spreaded all over the wire. Amperian loop is having radius less than the radius of the wire. So current enclosed by the Amperian loop will be less than I. Okay, so current enclosed IE in this case is less than I as shown in the figure 4.13. Since the current distribution is uniform, okay, so as I have already mentioned that current distribution is uniform, the current enclosed is IE. Current enclosed is equal to I into, we have to take the ratio, area of cross section enclosed by Amperian loop upon total area of cross section of the wire. Okay, so we have to take the ratio that what amount of area of cross section is enclosed by the Amperian loop upon total area of cross section of wire. Now you may have thought that why we didn't apply this ratio in the first case, because current is only flowing through the wire, not outside the wire. That's why for second loop, second Amperian loop labeled as 2, current enclosed is the total current I that is flowing through the wire. But now Amperian loop is having radius less than the radius of wire, so current enclosed by the Amperian loop will be less than total current. So now we have to apply this ratio. We have to multiply total current with this ratio. So what is the ratio? Area of the cross section enclosed by Amperian loop upon total area of cross section of wire. Okay, that is the enclosed current by the first Amperian loop. So IE equal to I pi r square upon pi a square. Okay, so I r square upon a square. Okay, current is flowing, current is basically the charges flowing through the perpendicular cross section in a given time. Okay, so that's why we are taking the ratio of areas, area of cross section. Okay, So because current is flowing perpendicular to area of cross section, and we measure the current also perpendicular to the cross section area. That's why we are taking the ratios of areas. Okay, so it is spreaded uniformly. Okay, so that's why it is in Amperian loop, its value will be fixed. Okay, because it is uniformly spreaded. So that's why area of cross section of enclosed by Amperian loop upon total area of cross section of wire. So after putting the value pi r square upon pi a square, enclosed current will be equal to I r square upon a square. Okay, now we have to put this enclosed current value in the Ampere circuital law. Using Ampere's law for a long straight wire, that was BL equal to mu naught I. So here L is again 2 pi r here is now radius of the Amperian loop 1. In first case, R was radius of Amperian loop 2. Now R here is Amperian loop, radius of Amperian loop 1 equal to mu naught I enclosed. What is I enclosed in this case? I r square upon a square. Okay. Now after rearranging, we will find the value of B. B will be equal to mu naught I upon 2 pi a square into R. Okay. So mark it as 4.15 B equation. Now you can see current is constant, A is constant, radius of wire is constant. Okay. Another all the things are constant. Rather only r, small r is variable because the distance from center of the wire to the surface of the wire can change inside point. It can be anywhere. It can be near center, it can be near surface, or in between surface and center. Okay, so r can be varied. So for now we have concluded the result for the point inside the wire. So magnetic field at a point inside the wire is directly proportional to the distance of the point from the center. Okay. So from this relation, we have concluded that B directly proportional to R, where R is less than A. For an inside point, magnetic field is directly proportional to the distance of the point from the center of the wire. Now we have to plot a graph that is asked in question. Therefore, conclusions drawn from this problem are given as B is directly proportional to R when R is less than A for inside point, and B is directly, magnetic field is directly proportional to 1 by R, or we can say B is inversely proportional to R when R is greater than A, outside point. Okay, so this is the plot. You can see in graph there is a y-axis marked as magnitude of magnetic field and x-axis is marked as distance from the center of wire. Okay, there is A also on the x-axis. A is the radius of the wire that is at surface. So B is directly proportional to R. So as R is increasing, B is increasing till surface, till the surface. So at surface, the magnetic field will be having maximum value. Now for outside point, beyond surface, it will decrease because it is inversely proportional to R. So it will go like that, shown in the figure. So that relation is hyperbolic and that is linear. Okay, so that type of plot is there. So figure 4.14 shows a plot of magnitude of B with distance R from the center of the wire. The direction of the field is tangential to the respective circular loop 1 or 2. Okay, so direction of field will be tangential to the Amperian loops. Okay, at that point we can find the direction of magnetic field that is tangential to the circular loop or Amperian loop. Okay, now what is the direction? It is tangential, but in which direction? So that direction you can find at any point on the loop is given by the right hand thumb rule. And this example has the required symmetry that makes it easy to use Ampere's law. So it is cylindrical wire. and the magnetic field around it is in the form of concentric circles. So that symmetry, that is the required symmetry, which makes it easy to use Ampere law in this case. Okay, magnetic field is maximum at surface and minimum at center. So now, next topic is the solenoid or magnetic field at the center of a long solenoid. So this is the application of Ampere circuital law. So despite being not applicable to find field at center of circular loop, that is the limitation of Ampere circuital law that we have discussed yesterday, that it cannot be used to find the field at the center of circular loop. But Ampere's law has numerous applications. So Ampere's law, circuital law, can be applied to a large number of situations of high symmetry, like straight wire. And another application is the law proves particularly useful for commonly used magnetic materials like solenoid. So to find the magnetic field at the center of a long solenoid, we can use the Ampere circuital law. So you can see in the diagram, figure 4.15a, the magnetic field due to section of the solenoid which has been stretched out of clarity, only the exterior semicircular part is shown. Okay, so this is the magnified view in the A diagram. This is the particular section of the solenoid, and it is only exterior semicircular part. Okay, notice how the circular loops being neighboring turns tend to cancel. So that thing we are going to discuss, that how neighboring loops are magnetic field due to neighboring loops are cancelling out. Okay, so you can see in the A diagram there is a magnified view of semicircular part. Okay, and at the end of the semicircular parts you can see there is a loops. That loop is magnetic field lines. That circular loops are magnetic field lines due to the current flowing through that solenoid. Okay, so this is the magnified view. Now at B part you can see magnetic field of a finite solenoid. That is the magnetic field lines due to whole solenoid. So you can see in the solenoid there are blue dots. In the upper part, in the B diagram upper part there are blue dots, and in the lower part there is cross. Okay, there are cross, and in the upper part there are blue dots. So that dot is representing current flowing through the solenoid in the outward direction, perpendicular to the plane and outwards. And that cross in the lower part are showing current is perpendicular to the plane and going inwards the plane. Okay, that is the sign convention for the current. So they have not shown the windings of the coil of the solenoid, but they have shown the current flowing through it. Okay, to prevent the mixture of the diagram with magnetic field lines and current and windings, they have made a simplified diagram only showing the direction of current through the solenoid. Okay, so you can see in this diagram windings are also shown, but in this diagram there are dots shown. Dot means this winding, like you can consider this winding in the A diagram. Current is going, flowing outwards and perpendicular to the plane in the upward section, like this dot. And in the lowermost end of the winding, current is flowing perpendicular to the plane and inwards. That is shown by cross. Okay, now you can understand. This is the pattern of magnetic field lines inside and at the ends of solenoid. Okay, now we shall discuss a long solenoid. Okay, so we are not going to discuss a short solenoid. We shall discuss a long solenoid. That is the assumption. What is long solenoid basically? That doesn't mean that it will be of length 1 kilometer. That is not meant by this long solenoid. In a long solenoid, length is significantly larger than radius. That means radius will be very, very small and length will be significantly larger than radius, relatively larger than radius. It can be 1 meter, But if radius is 1 centimeter, then that 1 meter of length is very much large as compared to radius. Okay, 100 times large than radius. That means long solenoid. Okay, long solenoid means it doesn't mean that length is very large of 100 meter, 200 meter. No, it means that length is significantly larger than radius. Length is relatively larger than radius. In a long solenoid, length is significantly larger than radius. A long wire is wound in the form of helix. Okay, so in the form of helix, like spring, you may have seen. Spring is wounded like a helix. Okay, so helical path, we have discussed the helical path of the charged particle also, and you know the what is helical winding, like in the spring. So it is wounded like in the form of helix, and neighboring turns are closely spaced. That is, it is closely wound. That means there is not much space between the subsequent windings. Means these two windings, like in A diagram, there is a distance between the windings, but it is shown to for a simplicity. But in actual condition, there is very much smaller distance between the windings. Okay, sometimes it is negligible. Windings are very closely wound. Okay, so the turns are closely spaced. Turns of the solenoid are closely spaced. Since turns are closely wounded, each turn can be regarded as circular loop. Okay, so their linear distance when we travel from one end to another end of the winding, their linear distance traveled is negligible because they are closely wound. Okay, if we cover one circle, the linear distance traveled is very much small because they are closely spaced. That's why each turn can be regarded as circular loop, not a helical loop. Okay, so since they are closely wound, each turn can be regarded as circular loop. So the net magnetic field is the vector sum of fields due to all the turns. Okay, so now you can see in this diagram. So there are magnetic field, there are loops of magnetic field due to this current flowing through it. And this direction of this magnetic field loops can be found using right hand thumb rule. Okay, you have to point your finger in the direction of current, and the curl of finger will give the direction of magnetic field. Okay, so in upper windings, in upper ends, you can see in the A diagram, or you can see in the B diagram. For now you can see in the A diagram, 4.15 A diagram, the upper end of the windings. In this upper end, the current is flowing perpendicular to the plane and outwards. So you have to point your thumb perpendicular to the plane and outwards and curl your fingers. Your fingers are curling in anti-clockwise direction. Okay, so you can see also the magnetic field lines are shown in the form of concentric circles, and direction of magnetic field is shown anti-clockwise in the upper end of the winding in the A diagram. Okay, in the lower end of the windings, current is flowing perpendicular to the plane and inwards. So you have to point your thumb perpendicular to the plane and inwards and curl your fingers. Now you can see your fingers are curling in clockwise direction. Okay, so you can see in the diagram also. So now you can see the magnetic field lines, the concentric circles, okay, or magnetic loops, the due to subsequent winding are cancelling out. You can see first two windings. In the upper part, in the upper end of first two windings, magnetic field line in the right of the first winding is going upward in this section, and magnetic field line in second winding in the left side is going downward. So both the magnetic field lines are in the opposite direction due to subsequent windings. Okay, since current is flowing through the solenoid is same, I current is flowing through all the windings. Okay, so magnetic field, strength of magnetic field will be same at the ends. Okay, so magnetic field here for first winding, in the right of the first winding, magnetic field is in the upward direction. In the left of the second winding, magnetic field is in the downward direction. So the magnetic field due to both these windings will cancel out in outside the solenoid, not inside, outside the solenoid. Okay, but inside it will add up because magnetic field is in same direction. It is going from left to right. Inside the coil, inside the solenoid, magnetic field due to all the windings is from left to right. So it will add up and combined magnetic field will induce. That is much greater than, because also radius is very small. So that added up or combined magnetic field will be in small space. So its strength will be larger. But in outside, there is free space. So magnetic field lines will be farther apart, or some most of the magnetic field lines are cancelled by each other due to the subsequent windings. Okay, due to the nearby windings. So magnetic field outside the coil will be very, very less, or inside the coil will be very, very large. So net magnetic field is the vector sum of fields due to all turns. So if we are going to calculate the net magnetic field in at the center of the coil, inside the coil, that will be due to vector sum of the fields due to all the turns. Okay, so magnetic field produced by all the turns will be added up, but it is a vector quantity magnetic field, so vector sum of the field, not simple algebraic sum. So enameled wires are used to insulate the turns from each other. Now, you may have thought that wires are closely spaced. There may be short circuit. Okay, because current is flowing through all the windings. If windings are very closely spaced, they are touching each other, so there may be short circuit. Okay, so they are enameled. Okay, means they are coated with some insulating material. So enameled wire are used to insulate the turns from each other so that they cannot interact when they are closely wound. So enameled wires are basically copper wires coated with a very thin layer of insulating material. So very thin layer of insulating material is used to enamel the wires to prevent the short circuit. So enameled wire are basically used to prevent the short circuits and to allow the more turns of wire to fit in a smaller space. That means if we want to fit the windings, fit the solenoid, or fit more turns in a smaller space, so we have to wound it closely. We have to touch it. Okay, so uh, all the windings should touch because they are closely wound, but they are not enameled, so it will result in short circuits. So to prevent short circuit and to allow more turns of wire to fit in a smaller space. Okay, so that are the two benefits of enameled wires. So figure 4.15 shows the magnetic field lines for a finite solenoid. Okay, so figure 4.5 is showing the magnetic field lines. I have already mentioned that are the pattern of magnetic field lines due to a finite solenoid, but means not infinite. From figure 4.15a, it is clear that field between neighboring turns cancel out outside the coil. Okay, that things I have mentioned that are going to repeat again. So I am explaining again. So it is clear that field between neighboring turns. Now you can see I have explained that due to this first winding, magnetic field on the right of the first winding is in the upward direction, or magnetic field in the left of the second winding is in the downward direction. So they will cancel out outside the coil, not inside the, because in the outside space there is more space, free space. So magnetic field will cancel out in the outside. In the inside of the coil there is very much small radius of the coil. Okay, so due to which magnetic field is added up inside the coil, not cancelling outside. So it is clear that field between neighboring turns cancel out outside the coil. Magnetic field lines created by each turn have opposing direction in the space outside the coil. So outside the coil, the magnetic field lines having a direction opposing each other. Okay. So you can see second and third winding also. So magnetic field lines due to in the right of second winding and left of third winding is in opposite directions. Okay, so they will cancel out outside the coil. So magnetic field lines created by each turn having opposing direction in the space outside the solenoid. From figure 4.15b, now we are moving to B point, B diagram. So at interior midpoint P. So in the interior, you can see the P point, which is midpoint. That is midpoint here in the interior. Okay. So field is uniform, strong, and parallel to the solenoid axis. Okay, you can see in the midpoint. Field lines are closely spaced. That means field is strong. Is uniform. They are farther apart by the same distance. There is no non-uniformity here. Where is non-uniformity? Outside. Now outside you can see difference between two field lines. First two field lines is different from distance between second and third field line. So there is non-uniform magnetic field outside the solenoid, but inside the solenoid they are closely spaced and equally spaced. So magnetic field is uniform, strong, and you can see it is parallel to the solenoid axis. So solenoid axis is this axis, horizontal axis. So magnetic field inside at interior midpoint P is field is uniform, strong, and parallel to solenoid axis. Combined magnetic fields from multiple coil turns create a stronger total magnetic field. As I have already mentioned that due to this all the windings, the magnetic field is added up. Combined magnetic field from multiple coils turn create a stronger magnetic field inside the solenoid. Okay. Now at exterior midpoint Q. Now we are going to discuss about exterior Q point here. The field is weak. As I've already mentioned, you can see the field lines are farther apart. Okay, and also non-uniform. So at exterior midpoint Q, the field is weak. Also maintains, but it is maintaining axial distance without perpendicular component. Rather, it is weak, but it is axial, not perpendicular. At Q point, you can see there is no perpendicular component of the field. At Q point, there is only horizontal component of the field. So maintains the axial direction without perpendicular component. As solenoid is made longer, it resembles a cylindrical metal sheet. Okay, as we are going to derive for long solenoid, that means length is significantly larger than radius. So it resembles a cylindrical metal sheet. The field outside the solenoid is very weak and shall be considered zero. Okay, so they are cancelling each other. Field lines due to subsequent or nearby windings is cancelling out. Not completely, but mostly cancelling out. So field outside the solenoid is very weak and shall be considered zero. Field inside becomes parallel to the axis everywhere. For a long solenoid, this is some short solenoid, but for a long solenoid, so this field lines are parallel for a long distance. So for the field inside becomes parallel to the axis everywhere for a long solenoid. So this is the another diagram, figure 4.16, the magnetic field of a very long solenoid. Okay, means radius is much smaller than the length. We consider a rectangular Amperian loop A, B, C, D to determine the field. Now you can see this is the sectional view of the solenoid. Solenoid is cut from the half and it is a front view of this other half. So this is a sectional view. Means these dots in the upper section, they are representing that current is flowing perpendicular to the plane and inwards, or sorry, outwards. Okay, so these are the windings, but windings are not shown for simplicity of the diagram. So these dots are currents that is flowing in the windings perpendicular to the plane and outwards, and that crosses are also showing currents in the windings that are perpendicular to the plane and inwards. Okay, now this is the why this hand is shown for right hand thumb rule. I will explain this later. So I have chosen a Amperian loop A, B, C, D to determine the magnetic field at the center of the loop. Now consider a rectangular Amperian loop A, B, C, D. The field along CD is 0. Why field along CD is 0? Because we have assumed, we have taken an assumption that field is very weak outside the loop, outside the solenoid. That's why along this CD there is 0 magnetic field, because outside the solenoid field considered is 0. That's why field along this CD section that is outside the solenoid is 0. Transverse section BC and AD. So these transverse section BC and AD have 0 field components, making no contribution in the magnetic fields. So due to this magnetic field is, this CD section is half outside, half inside, and the inside part of this CD, you can see, sorry, CB, you can see magnetic field is perpendicular to this section. Okay, so we have discussed in the Amperian circuital law that we have to choose a Amperian loop. We have discussed the case where Amperian loop is where magnetic field is tangential to Amperian loop. We are going to consider that case only, when magnetic field is tangential to magnetic field. Okay, here for this BC section and AD section, magnetic field is perpendicular to these sections. Okay, and you can also solve this by formula B dot dl. B dot dl means BDL cos theta, and the angle between this magnetic field and this dl means this along length is 90 degree. So BDL cos 90 degree will be 0. That means magnetic field due along these two sections BC and AD is 0, because they are perpendicular to the magnetic field. So here magnetic field only have the horizontal component, not perpendicular component. So transverse section BC and AD have 0 field components along them, making no contribution in net magnetic field. So along this CD, magnetic field is 0. Along this BC and AD, magnetic field is also 0 due to perpendicular components of magnetic field doesn't exist, making no contribution in the net magnetic field. So with field only, what section is remained? Only AB section. Okay, so with field B along the AB section, the relevant length of Amperian loop is L equal to H. Now the length that we are going to consider in this problem is only H, that is of CD or that is of AB. Only H length will be considered. There it is a rectangular loop, but length of this AD, BC and this CD will not be considered because magnetic field along these sections is 0. Only length of AB is being considered, and the relevant length of Amperian loop will be L equal to H, and field is along AB only. Now let n be the number of turns per unit length. You can see what is small n, be the number of turns per unit length of the solenoid. Okay, means for a unit length, what number of turns are there? Okay, and total number of turns in this loop is, in this AB section is, n is the number of turns per unit length into the length of this section of loop. So that is the total number of turns through this section of loop, through this section of Amperian loop. That are the total number of turns is N into H. The enclosed current is, what is the amount of enclosed current? From each winding, from each turn, current flowing is I. So if NH is the number of turns through this section, so what is the enclosed current in this section? Will be I into NH. Got it? What is the number of turn in this section of loop? NH. So enclosed current, each winding is having current I. Okay. So what number of turns or windings are there in this section? NH. So what is the enclosed current? I into NH, where I is the current in the solenoid or in the each turn of the solenoid. Applying Ampere circuital law, equation 4.13b, BL is equal to mu naught IE. Okay, so this is the Ampere circuital law. Now L here is H. Okay, because section which is relevant length of Amperian loop is H. So L here is H. What is I enclosed? I N H. So put this value in this equation. So BH is equal to mu naught I N H. So H and H will get cancelled out. And this is the final expression for magnetic field at the center of inside and center of solenoid, long solenoid. So mu naught Ni. So magnetic field inside the long solenoid. So this is the expression for long solenoid only, not short solenoid. Okay. So B equal to mu naught Ni. What is N? N is not number of turns. N is number of turns per unit length. Okay. So you have to remember that thing while doing the numerical. So mark it as 4.16. Direction of field is given by right hand thumb rule. Now, right hand is shown in the figure also. So you have to see what is the direction of magnetic field at the center of the coil. So you have to curl your fingers. Now there are number of windings and current is changing direction according to the windings. So you cannot find the magnetic field at each point. So you have to curl the fingers. Now you have to replace the terminology. Now what we were doing, we were pointing our thumb in the current direction and curling the fingers to find the magnetic field direction. Now you have to curl the finger in the direction of current and thumb will give the direction of magnetic field. These two physical quantities for right hand thumb rule can be interchanged. Okay. So now you can curl your fingers in the direction of current and thumb will give the magnetic field direction. If you are pointing your thumb in the current direction, then fingers will give the direction of magnetic field. If you are curling your fingers in the direction of current, then thumb will give the direction of magnetic field. Okay. So this can be used interchangeably. So in the one phase, in the one end of the loop, you can see what is the direction of current from that side where this hand is shown. Current is going outwards from upper part and going inwards in the lower part. So from, if you are seeing the solenoid from this hand side, you will see the current is anti-clockwise. So curl your fingers in the anti-clockwise direction as shown in the figure at that end of the solenoid. Thumb is pointing away from the solenoid. That means magnetic field lines are, direction of magnetic field lines is perpendicular to this cross section of solenoid and outwards. If you are seeing this solenoid from this end, from the other end, now you can see current is flowing, going outwards from the upper section and going inwards in the lower section. So curl your fingers from that end. Now you will see that magnetic field direction is towards the solenoid, from other end, from that end towards the solenoid. That is, magnetic field lines are entering from this end and leaving from, magnetic field lines is entering from this end and leaving from this end. Okay. So these these magnetic fields are resembling somewhat the magnetic field pattern due to a bar magnet. There is one north pole, there is one south pole. Magnetic field lines exiting from north pole outside the magnet and entering south pole outside the magnet. In the outside of magnet, bar magnet, magnetic field lines is directed from north to south. It is showing similar to that. Now you can see I have mentioned in the previous lecture also. If you are seeing this end of the solenoid where hand is drawn, you can see magnet current is having direction at that end is anti-clockwise. So for anti-clockwise direction, the pole formed is north pole. And if the current direction from any end of the solenoid is clockwise, so that pole will be south pole. If the direction of current is clockwise, then pole is south. If anti-clockwise, then pole is north. Got it? So direction of field is given by right hand thumb rule. Solenoids commonly generate uniform magnetic fields. Field strength can be enhanced by inserting soft iron cores inside the solenoid. So field strength can be enhanced by inserting soft iron core that we are going to discuss in our upcoming chapter magnetism and matter. So the example, a solenoid of length 0.5 meter has a radius of 1 centimeter and is made of 500 turns. It carries a current of 5 ampere. What is the magnitude of magnetic field inside the solenoid? Okay, firstly you have to find is it long solenoid or not, because the formula B equal to mu naught small n I is valid for long solenoid. Okay, so number of turns per unit length you have to find also, because in question only number of turns is given. We have to find the number of turns per unit length that is required in the expression of magnetic field. So that is n equal to number of turns per unit. What is the length given? 0.5 meter. So 1000 turns are available for 1 meter. So what are the number of turns per meter? 1000 turns per meter. Length is given 0.5 meter and radius is given 0.01 meter. So take the ratio L by A, 0.5 upon 0.01 equal to 50. That is length is 50 times the area. Okay, that means length is 50 times the radius. Okay, so that ratio is very large. That means length is much greater than radius. Okay, so length is much greater than the radius of the solenoid. That means it is long solenoid. Now we can apply the formula B equal to mu naught Ni. So hence we can use the long solenoid formula, namely equation 4.16. So B equal to mu naught Ni. So what is the value of mu naught? Is 4.10 to minus 7. What is the number of turns? That was 1000 10 to power 3 into what is the current flowing through? That is 5 ampere. So B is equal to 6.28 into 10 to power minus 3 Tesla. Okay, so that is the answer. That is the magnetic field inside the solenoid. So let's have a quick recap. Magnetic field due to current I flowing in a thick wire. Okay, that is the expression for thick wire. That example we have done in the beginning of the lecture. That is the theory for that lecture. Okay, so magnetic field varies linearly with R inside the wire. That is, R is distance from the center of wire, less than capital R. Capital R here is radius of wire. So if there is an inside point, then magnetic field varies linearly. That means B is equal to mu naught I small r upon 2 pi capital R square. So where R is the distance from the center and R is wire's radius. Field decreases as 1 by R outside the wire. For outside point of the wire, field is related with distance as inversely proportional. So field decreases as 1 by r outside the wire, that is for r greater than capital R, means for distance greater than radius, that is outside point. So magnetic field is given by mu naught I upon 2 pi r, where r is distance from the center. Maximum field occurs at the surface, that is small r when small r is equal to capital R. So magnetic field lines are circular around the wire. Okay. Magnetic field due to current I flowing in the long solenoid. Field inside is uniform and parallel to axis. Okay, so in a long solenoid, the magnetic field inside is uniform and parallel to axis. Strong, uniform and parallel to axis. That is B equal to mu naught N I, where N is number of turns per unit length. Field outside the solenoid is negligible, very weak. We can consider it as 0. Field strength depends on current I and turn density N. What is turn density? Number of turns per unit length. So field strength depends on that according to expression. If number of turns per unit length is greater, then magnetic field produced will be greater. If current flowing through the solenoid is greater, then magnetic field inside the solenoid will be greater. And field lines due to solenoid are similar to bar magnet pattern. As I've already mentioned that field lines due to solenoid are similar to bar magnet pattern. There are some practice questions you are going to do yourself. Explain why the magnetic field inside a thick current carrying wire varies linearly with radius r, while outside the wire it decreases as 1 by r. Support your answer with the relevant equations. Second, a thick wire of radius capital R carries a current I uniformly distributed across its cross section. At what distance from the center of the wire is the magnetic field maximum? Okay, these two questions I have explained in summary also. In applying Ampere's law to a thick wire, why do we only consider the current enclosed by the Amperian loop rather than the total current in the wire? Okay, that thing also I have mentioned. Why we are considering only the current enclosed by the Amperian loop. Compare and contrast the magnetic field patterns inside and outside a solenoid. Give expression of magnetic field inside the solenoid. Okay, so pattern you have already seen in the diagrams, and you have to give the expression. What is the expression? You already know. Got it? So thank you, but please wait for the DPP section. For a long straight wire with current I uniformly distributed, what is the magnetic field at a distance less than r less than a, where a is the radius of wire? So which expression we have discussed for inside point? So you have to comment me the correct option as fast as possible. I will mark the answer based on your understanding. Which expression is for inside point? First, second, third, or fourth? Okay, second. Which symmetry is exhibited by the magnetic field of an infinite straight current carrying conductor? Spherical symmetry, cylindrical symmetry, planar symmetry, or no symmetry? For a straight current carrying conductor, what is the symmetry exhibited by the magnetic field? According to right hand rule for a straight current carrying wire, if thumb points in the current's direction, finger show electric field direction, magnetic field direction, force direction, or current density direction. Which is the correct option? This is very simple. Yes, second. Ampere circuital law is analogous to which law in electrostatics? Coulomb's law, Gauss law, Faraday's law, or Ohm's law? Gauss. Ampere circuital law is given by which equation? This is EDL mu naught I. This is BDL mu naught I. This is BDA mu naught I. This is EDA mu naught I. This is integral. First option is integral E dot dl equal to mu naught I. Second option is integral B dot dl equal to mu naught I. Third option is integral B dot dA equal to mu naught I. Fourth option is integral E dot dA equal to mu naught I. Which option is correct? What was Ampere circuital law? B dot dl, integral B dot dl equal to mu naught I. Okay. Second option is correct or not? Yes. So all options are correct. Well done. Okay. Thank you. I hope you enjoyed the session.